is also the same as n equals 2 minimal model, which is well known, exactly solvable rational conformal field theory, and those details will be relevant for computing to study the spectrum as well as the dynamics of these little strings. This part is described roughly by this. The picture will be this cigar CFT, the cigar. And this is the more difficult part. And we know a lot about this, but we're going to be interested in certain vertex operators and their correlation functions in this cigar CFT, not all of which are known yet, and we'll try to understand what they are. In this, I should review the construction of this cigar coset CFT in some detail in order to explain my notation. So let's start with SL2 W0 model. So here I'm going to start with a supersymmetric SL n equals 1 SL2 level K. As I mentioned last time, you start with n equals 1 supersymmetric SL2 W0 model. If you do the coset, you actually get enhanced n equals 2 superconformal theory after doing the coset. So the SL2 W0 model consists of currents JA, where A ran through 1 to 3, let's say, with the OPE JAZ, JB0, it's going to be some eta AB over to Z squared plus some I epsilon ABC over Z JC 0, where eta AB is of signature 2, 1. Order. Eta AB is this 1, 1, minus 1. And then there are, there's a level here, which is K plus 2. This is for the bosonic part. Actually, my notation. I should call this lowercase j for now. Lowercase j, these JA, JBs are bosonic SL2 currents at level K plus 2. There are 3 fermions, lambda A, 3 fermions. These are free fermions. And one can form a overall diagonal SL2 current, set of SL2 currents. Sorry, these 3 fermions, once again, are going to obey some OPE, but of the non-standard signature, it's going to have this 2, 1 signature, so like eta AB over Z. So lambda 3 is like I times the usual free fermion. And then one can form a diagonal SL2 current, which is a combination of this JA with the fermions, minus I over 2, epsilon ABC, lambda B, lambda C. So these are the set of SL2 currents at level K. One can also write down some n equals 1 super conformal current in this theory, which I won't bother writing down now. Okay. Now, the primary operators with respect to this SL2 current algebra are labeled by J, M, and bar. I'll call these phi, J, M, and bar. As I mentioned last time, this operator will have conformal weight minus J, J plus 1, plus M squared over K, and similarly for the right conformal weight with M replaced by M bar. These things, so here, J can either be a minus 1 plus purely imaginary number, or J could be real, but if J is real, one has to be, well, if J is real, then a priori these are just entirely non-normalizable vertex operator. Sorry, so that's wrong. There's no M squared here for the SL2 primary. That was an error. The shift by M squared over K, that was after doing the coset construction. Before the coset, it just depends on the Casimir. And this M and M bar are the spin with respect to the J3 component. J3 on the left and J3 bar on the right. Third component on the right, SL2 current algebra. Okay. Now, I'm going to organize these primaries in the following fashion. So, the sigma on SL2 by the Wick rotation can be also related to sort of the sigma model with H flux on the just a Euclidean three-dimensional hyperbolic space. So the kind of Euclidean continuation of this SL2 WZ model is called the H3 plus model. The distinction is a bit subtle. It has to do with what, at practical level, it's a question of what operators you want to include in your spectrum. But in any case, here we can write down the action of this WZ model in the following form. So K times integral the Walsh action partial phi partial bar phi plus e to the 2 phi partial gamma partial bar gamma bar. So this is the actual one way to write Walsh action for this Euclidean continuation of SL2. This gamma is a complex field. So this is basically a Poincare ADS3. Euclidean ADS3 is a phi direction. And then there's this plane with complex coordinate gamma. The procedure through which we do the cosine construction is that, so here, let's say you pick a point at origin on the boundary of this ADS3, and there's a kind of isometry that expands around that point. One can gauge that that isometry. So practically what I mean is you replace this action by coupling to a gauge field, replacing this by partial phi plus gauge field AZ components and partial bar phi plus AZ bar. And also here, the taking account of the gauge field generates the isometry that expands, corresponds to shifting phi and also expands in the gamma direction. So this write gamma as rho e to the I theta. This becomes e to the 2 phi partial rho plus rho AZ plus I rho partial theta. And here I have partial bar rho plus rho AZ bar minus I rho partial bar theta. I should mention that if you look at this is not a standard nonlinear sigma model because it's H flux. This is, gamma is complex. Okay, so if you can integrate out a z a z bar and work in the gauge rho equals 1, just at the classical level, you reproduce. I mean, it's a simple exercise I won't do on the board, but just extremize this action with vector A. You'll find that this becomes. This will then be described by the linear sigma model on the two-dimensional target space, which has the metric ds squared is d phi squared plus d theta squared over 1 plus e to the minus 2 phi, straightforward calculation. And if you make a redefinition, phi equals log of sine rho, then this metric becomes d rho squared plus tanh square rho d theta squared. So this is the cigar geometry. So this is how you understand that the cosine is described as cigar, and there's a linear dilettante, no, sorry, not linear, it's a dilettante, non-trivial dilettante profile that arises from the one loop determinant as you integrate out the gauge field. Now, the cigar CFT is a theory of interest, but it's related in this way. And a useful way to organize the primaries of the H3 plus model is the following. So let me write, one can organize this phi, j, and bar, function of z, in terms of kind of generating operator, if you wish. You can write this through a Laplace transform, d squared x j plus m, x bar j plus m bar, phi j as a function of this complex parameter x and z. And then this phi j x z has a nice interpretation. This is much like how you would just write down e to the ikx kind of operator in the nonlinear signal model. So here, the phi x, so semi-classically, phi j x z will be described by a wave function on this Euclidean ADS3, which is of the form gamma. So this wave function is going to be will be a function of gamma and phi. So the function, which also depends on x, which is simply gamma minus x squared e to the phi plus e to the minus phi, the power minus 2j minus 2. And if you calculate Casimir made out of the SL2 isometries, I can let you reproduce the conformal weight. Okay, so that's a way to understand what these operators are. And here you see very clearly that asymptotically, this phi is basically the same as rho. And so down the cigar, so in the asymptotic region of the cigar, these things typically blow up exponentially. But if you look very carefully at some discrete values of j, you'll discover solutions to the wave equation that's actually localized at the tip of the cigar. So that's something that can only be seen by carefully analyzing the full exact reflection coefficient at the tip of the cigar, and you'll be able to identify those modes. And those are the modes that are going to be of interest to us, because as I mentioned, for the cigar CFT, there are modes that can propagate down the cigar. These have the interpretation as instant strings, and as they move down to the asymptotic region of the cigar, the corresponding instant strings in the 60 Yang-Mills theory become very thin. Whereas on the other hand, at the tip, there are modes that localize the tip. These are the modes that are trapped in 6 dimensions. In particular, they'll be massless. The modes that are massless in 6 dimensions, which correspond to the U1 to the k-1 massless gluons on the Coulomb branch of 6D gauge theory. The gauge theory picture, let me, here. So on the string theory side, we have this Walshy description, and on the gauge theory side, what this describes in the IR limit would be 60 super Yang-Mills, 1,1 super Yang-Mills, 60 supersymmetries on its Coulomb branch, where, so in some particular vacuum, where the 4 scalars, 4 adjoint scalars in this super Yang-Mills theory acquire some expansion value that correspond to the transverse position of the stack of k in its phi branes. As you might remember, so there are 2 R2s. There's R2 times another R2. That's the Coulomb branch, and the k phi branes are sitting at the origin in 1 R2 and spread out on a circle of equal distance on the other R2. Here I draw the example of k equals 6. Okay. So of course you can move this thing around that corresponds to deforming that CFT, but the point where we know the exact description as this is when there's a ZK symmetry. Now, there's a ZK symmetry that permutes cyclically this k in its phi branes, and that symmetry corresponds to the symmetry that assign different faces to the orbifold twisted sector of this ZK. So before this orbifolding, you have each of these theory has some discrete ZK symmetry. Now when you do the orbifold by the ZK, that symmetry is gone, but then you're left with another ZK, perhaps I should call this ZK tilde, that corresponds to, so whenever you do a ZK orbifold, there's, now the original ZK is gone, but you have a new ZK symmetry that assigns different faces to different orbifold twisted sector. That's the ZK tilde here. And also, there's a funny business here, which I'd like to just to mention. If you recall the argument based on supergravity where one obtains the cigar, they are considered smeared NS5 brane, where you think that the NS5 brane is smeared around the circle, and the zk turns into u1. But how come that, how come we recover the zk at the end? This was explained in a nice paper by David Tong some years ago. It has to do with the worldsheet instant effects. So it's a rather subtle story, just to mention that. So in any case, the point is that if we are interested in studying the scattering of the massless modes of this 60 gauge theory on the Coulomb branch, well, I mean, this is only a low energy effective description. In general, you might also have higher dimension operators, which we might have to worry about. We'll discuss that towards the end. So the massless degree of freedom will involve some u1 to the k minus 1 photons. I mean, the center mass degree of freedom is going to be factored out. And we have k minus 1, this is SUK, 60 superambulance theory. So there will be these k minus 1 abelian vector multiplets. If you look at the scalars, there are these modes that if you look at gauge bosons, then there are these u1 to the k minus 1, u1 to the k minus 1 vector bosons, which come from sort of some. You can take linear combination of the abelian vector bosons on each of these fibrils in the type 2B string theory. And then there are also the scalars. The scalars correspond to the motion of the fiber in the transverse space. In this case, for example, we're factoring out the center mass degree of freedom. So this guy, if you move all the fibers in one direction, this mode is not allowed. This is over. This mode decouples, but there's for example, there will be a breathing mode that will be allowed. This breathing. So, in the case of the vector boson, on the other hand, so this breathing mode for the scalar is invariant under the zk. The stuff that's invariant under the zk corresponds to untwisted sector from the worldsheet description, whereas the things that, if you take some linear combination and pick up some phase, so some power of the kth root of unity, those will correspond to twisted sectors, twisted sector vertex operators in this description. For the vector bosons, actually, they're all the k minus 1 vector bosons are in the twisted sector. There's nothing from the untwisted sector. And that's because the untwisted sector will correspond to the combination of the vector bosons, of the k vector boson that's invariant under the zk, but that's the overall u1 that decouples. So the upshot is that you're expecting to have 4 times k minus 1 scalars, of bosons, and plus k minus 1 vector bosons, and also the fermions, but we'll discuss the scalar modes for the moment. And all the k minus 1 vector bosons are supposed to come from the twisted sector, but they're in fact in RR sector, whereas the scalars come from NS NX sector. 4 of them are in the untwisted sector, the remaining 4 times k minus 2 of them are in the twisted sector. So all of these features can be seen explicitly from the cigar CFT, but that's a story that's quite technical, and I will not spell it out all in complete detail on the board. You can find all the details in our paper, but one can identify all these vertex operators. Perhaps I should at least describe the construction of these vertex operators. This is kind of an important part of the story. First of all, I think I mentioned a little bit of this last time. The J3 can be bosonized by, my radius is minus some factor squared over 2 times partial x. And then you can write this phi j m bar as e to the square root 2 over k, n x minus n bar x bar. So there's a kind of a chiral boson coming from bosonization of the left J3 current of SL2. There's a right boson coming from the bosonization of J3 bar. And the thing that's left over, V, J, and M bar, this is a primary. Actually, this is a parafermion primary in the coset CFT SL2 mod U1. For the cigar CFT, it turns out that the allowed set of values for this V, J, and M bar, so M minus M bar will have the interpretation as some momentum momentum along the cigar, and M plus M bar is K times some 1D number. It has interpretation as a 1D number around the cigar. And as I mentioned last time, for the modes of interest, there are some modes localized at the tip of the cigar that correspond to some discrete set of finite discrete set of range of M, and correspondingly some discrete set of values of J. Okay. Are there any questions so far? These are not all the primaries. If I just have these, that won't give me the right set of vertex operators, the correct set of vertex operators. So just to explain how to actually write down the vertex operators of question here, one has to consider spectral flow. So we're talking about the coset theory, SL2, level K, mod U1. This is n equals 2 superconformal theory. It's a spectral flow operation that takes some operator of weight, let's say delta, and U1 R charge n equals 2 superconformal algebra. We'll shift these to some delta eta, R eta, which is R plus eta C over 3, C is central charge, which is, well, whatever that is. I wrote last time, it's 3 times K plus 2 over K. Delta plus eta R plus eta squared C over 6. Explicitly, the way this can be constructed is anyway, let me not even describe the explicit construction. You can take this multiplying some exponential operator that's constructed out of the bosonization of the fermions in that SL2 WZ model. And then if you apply the same procedure, you factor out the corresponding this kind of expression involving the appropriate charges, the U1 charges, then you're left over with some spectral flow operator, which I'll denote by V, J, M bar, eta bar, or spectral flow parameter on the left and on the right. Okay, and one can write down the, so these vertex operators have some conformal weight. In any case, let me write down the kind of class of vertex operators that will describe the at least the massless that will describe the massless degree of freedom of the six-dimensional theory. So massless vertex operators. I'm going to take, so there's this construction in SL2, and there's a similar corresponding construction in the SU2. In the SU2 case, this J and J will take half-integer value, and M ranges from minus J to J as usual. In SL2 case, as I mentioned, there was this very subtle story of what are the kind of discrete set of values of J that give rise to these normalizable vertex operators. So the general expression for the vertex operator of interest will have this vertex operator from the SL sector. So I denote this by VSL, which is the same thing as I wrote there, which will depend on eta bar, depend on some j, m bar, and then there's going to be same construction in the SU2 coset. So depend on some eta prime bar, depend on some j prime, m bar prime. And then you can form some vertex operator, say with e to the I p dot x in the R1, 5, and the p mu x mu. And you can have, let's say, as an example, in the Raman sector, you have a spin field S A dot. These are the spin fields in the R1, 5 direction. And then you have some ghost e to the superconformal ghost goes on the worldsheet. And 5 over 2 minus 5 tilde over 2. As usual for the Raman vertex operator in the -1/2, -1/2 picture. So this is the operator, the kind of operator of interest. It turns out that after some a very detailed analysis that I will not show you here, which you can find in our paper, the set of values of J and so one can identify precisely a set of this kind of vertex operators that describe exactly this set of the expected massless spectrum. They turn out to be the following. So these spectral flow parameter, yes.
So can you remind me what's A and A dot? On the S, what are those indices? S, A,
these are the spinor indices of SO1, 5. So since we're talking about,
are they SU, the little group like SU2 cross SU2 or?
yes.
Okay.
These are the little group. Yes. Thank you. So the spectral flow parameter will be integer for NS vertex operators. But it turns out in this context it's easier to work with RR vertex operators for some technical reason. I'll take these to be 1/2, and this, let me take these to be -1/2, and this J and M and N bar ranges over some set of values. By the way, here, when I say that the Wanting number is n plus n bar is a multiple of k, that was before the zk orbifold. So after zk orbifold, if you look at the zk twisted sector, this restriction is relaxed, and this m plus n bar can be any integer, not necessarily a multiple of k. Here, so the value j turns to be, let's say, call it L over 2, and m and n bar then take to be minus L plus 2 over 2 minus L plus 2 over 2. So here we have L minus L over 2 minus L over 2, where L ranges from 0, 1, 2, all the way to k minus 2. So these are a set of k minus 1 vertex operators, which are called V minus Raman, comma L. So this, I claim, is the set of Raman vertex operators that correspond to the k minus 1 vector bosons. In fact, the charge with back to zk tilde rotation turns out to be e to the 2 pi I over k times L plus 1. So all of these are in the twisted sectors, and they are rotated by this with some phase under the zk tilde rotation. Now, in these minimal models, and also in this coset, there's some identification. One can write down another kind of vertex operator called VRR plus L, which involves basically the same construction, but I convert this, flip the sign of all the eta bar, eta prime bar, and also n bar, n prime bar. So you change all the sign of this and change all the sign of this, you get the VRR plus. You might think that this gives you another copy of the vector bosons, but that's not true. There turn out to be identification of these, there's subtle identification among